we have a linear mapping that gets x to ax, which is basically multiplication by a matrix from the left side, this linear map. And let's say this A, we label F K2, K2. We make A equal to be the matrix 3, 1, 2, 1 or something, for example. And K2, K2 basically means the basis of 1, 0, 0, 1. And this is also a basis 1, 0, 0, 1. So what this means, this notation says, it's in respect to these two bases. And there is this interesting thing that helps us have a linear map and convert it for the case where inputs are in one basis, outputs are in another basis. And in such cases, we can derive some formulas regarding this. And let's say that now the A as we have it in this default setting is exactly written in terms of the coordinates of the normal basis. So they're in this default form, the most usual form. We can have nevertheless a different basis. And let's say, for example, we have, let's call it Y, capital Y1. That's one basis. Let's call that, let's make that 3, 2 and 2, 1. And Y2 would be a basis composed of 1, 2 and 1 minus 1. And these two bases, we want them to basically replace the K2 and K2 here, that if we had the linear map, input goes in one basis, for example Y1, and output should be outputted in Y2. So how we would write that is, we have F in this square bracket, and down here we write how we want to start the input, and here is the output, Y2. And there is actually a direct formula we can use, which basically is derived from the property of the whole matter. And that is, we can simply take the transition basis. So we can label it P Y2, take its inverse, then multiply by the original matrix, which we can label F K2, K2 in the canonical basis. And then multiply, these are a multiplication of three matrices. And on the right side, multiply by this change of basis matrix, just like this one was a change of basis matrix. But here, it's a change of basis matrix in respect to the first basis, the Y1. So of course, we had a default basis in which both the input and output were for initial A, F, K2, K2. And if we want to have A, F, Y1, Y2, we would basically use this formula for it. So we take in the middle is the matrix in the original form. On the right side is the transition to the matrix of Y2, to the base vectors of Y2, and left is the inverse of transition to the base vectors of, on the right is Y1, transition to the vectors of Y1, here is change of basis towards Y2. By transition, I mean the change of basis. And this is a thing that I would recommend knowing first, because this is a more advanced idea than change of basis merely. But let's just quickly go over it. So if we have P sub Y1, what it really means is we should take a matrix. It will end up being a 2 by 2 one in this case, of course. We're only dealing with square things here. 2 by 2 matrix here, then a 2 by 1 base vectors in both cases, of course. And we create a matrix where we put, in this column, we put Y1 expressed using E1 and E2, which are the two elements of K2. So in terms of the canonical basis. So if we want to express the Y1 first vector 3, 2 in terms of canonical basis, that's this one, when express it using K2, then we know, let's separate out a bit, that 3, 2 is equal to 3 times 1, 0 plus 2 times 0, 1. So we have 3, 2. So we just write 3, 2 here. So actually this is a trivial case, of course. And the same will go for the second one. It will be 2, 1. And the second thing is, for the change of basis for Y2, we will express in each column the corresponding vector. Here in the first column is vector number 1 of basis Y2 in terms of K2. So again, it will end up being 1, 1, 2, because that's how the trivial base works, the simple canonical base. So we just rewrite the columns of the vectors of the base of y2 here as well. And all we do then is use this formula. So we've established what it is equal to. So then all you have to also take is the inverse of y2, which